Yes, here we are once again, the physics video lecture, psci 168, video lecture 8. So where were we? We finally made it to the concept of energy. And everything we've done up until now was important and necessary, but we are now at work and energy. Let me go ahead and just write energy, work, and power. These three words, that's what we're going to be talking about today. So I'll go back to work for beginners to start with. It's a force times a displacement. Okay, so you move something against resistance, basically. And because of that, the force and the displacement have to be parallel, or we have to take parallel components. So I explained that last time. The units, we're talking about the units, we just put square brackets around. So if we have work as force times displacement, we want to know what the units are. We have newtons times meters, newtons times meter, and that's the joule. And of course, the example is lifting something up. And that's can't be overstated how important that example is, because we'll see it all through the semester. So the example, lifting a weight. Now, I mentioned at the end of the last hour, I want to talk about the stair climb. And so let's do just that. The stair climb, and we just draw some stairs here, draw ourselves here at the bottom, and then we make it up here to the top. Okay? So we've got this ground level, and remember when I was using the bowling ball, I showed that horizontal takes no work, then we do some work. And so the stair climb, we can think of it the same way. It's a bunch of horizontals that require no work, and the vertical, lifting our body, as it were, requires work. And so if we have a total height h here, then the work is just our weight, which we're going to still call F for force, times the height. Okay? So the work is equal to our weight times the height. So now's the time to plug in a number or two. So my example is going to be, for example, if my weight F is 800 newtons, and the height of the stairs h is 5 meters, then I would have 800 times 5 would be 4,000. Okay. Then the work equals 800 times 5 equals 4,000 joules. And I kind of chose that because we'll see later on that 4,000 joules is an interesting unit of energy. It's something that comes up a lot. Okay, so, but there's my stair climb. That's pretty average weight and stair climb, 4,000 joules. Okay. So what would another example be? A mountain climb would be the same kind of example. So, for example, a mountain climb, well, you may climb 1,000 meters in several hours or half a day or something. So h could equal 1,000 meters, and then the work would be the same 800 newtons times 1,000. Okay. It would be 800 newtons times 1,000 meters. You see the numbers are already starting to get big, but we know how to deal with that. That's 800,000, or that's 8 times 10 to the 1, 2, 3, 4, 5. So 8 times 10 to the 5 joules. And amounts of work are going to be even considerably larger than that. And so once we get into those larger numbers, we just multiply them out, but we use orders of magnitude and scientific notation. Okay, so the stair climb, and you can make up any number of examples that go beyond that. So we have energy and work. And what did I say about energy? I also had this at the close of the last lecture. Energy is more general than work. It's the capacity to do work. To do work. So that's why if we say food has energy in it, the reason is because, you know, we eat the food and somehow that enables us to climb the stairs. Or if we say fuel has energy in it, say gasoline, the idea is we can, by way of a mechanism, take the gasoline and the mechanism will then do that work, say driving our car up a mountain, up a hill, against some resistance. So energy, the capacity to do work. There's also an aspect of heat transfer when we get to thermal physics, but for now, we're just talking about energy, and this work is what we call mechanical work or mechanical energy. So energy is the capacity to do work. So you see the energy itself is not a thing. Okay. We'll see it's a relationship between things. So right now, this definition, the capacity to do work, should make good sense. So I have energy and work, and I'm immediately also going to define power. So we have my numbering things, why not? So now power. And a good example for the power is our stair climb again. We can imagine just walking up the stairs slowly, or we can imagine sprinting up the stairs. And we can imagine, say, a football player, someone who we say is powerful, sprinting up the stairs in a very short burst of energy. So when I define power, you'll see that that immediately makes sense. Power is equal to work per unit time. So it's work divided by time. That's the power. So the next thing I do is write this in symbols, and I put that square bracket around each side, which means I'm asking what are the units. And the units of work we just learned are joules, J. Units of time are going to be seconds, so that's joules per second. But that also has another name with which you're familiar, because a joule per second is a watt. So it equals watts. So the units of power are watts, and these are the same watts you're used to talking about on, say, a light bulb or some other device that uses so and so many watts. So joules per second is watts, and what we're going to do next is return to our stair climb and talk about the wattage, the power that's needed to climb some stairs. And by the way, that'll bring in the relationship with horsepower. You've heard of horsepower as well. So let's see, we're going to reproduce the stair climb in terms of this new concept, power is work per time. And I'm going to just redraw that picture. So my example is power to climb the stairs. So yeah, we'll draw the picture. We'll draw the stairs again. Why not? The bottom to the top here. Height of the stairs is h, and since the definition is work per time, p sub stair climb is going to be your weight times the height divided by the time. Okay. Still using force for weight. We'll change that later on, but right now weight is a force, as we know. So a good example would be to take those 4,000 joules. Let's do this again. 800 newtons times 5 meters. And we can divide by some time, say between 4 and 8 seconds. But you know, I'm just going to do 5 seconds. But yeah, we could use any time. If we take a whole minute to go up the stairs, so be it. Okay? But we're running up the stairs pretty quickly, 5 seconds. And so the units are watts, and I cancel the 5, those are easy numbers, so it's 800 watts. Now here's where I'll go ahead and put in something for comparison. 1 horsepower is equal to 746 watts. So there you have it. If you can run up the stairs faster than 5 seconds, or around 5 seconds, and you're 800 newtons heavy, then your output is 800 watts, and that's just roughly 1 horsepower. Of course, you can't do this all day, whereas a horse can deliver that kind of power, you know, all day, supposedly. And again, we're going to be able to have expressions for power that are much, much larger than this, and that are much, much smaller than this. But this is a human power output, well defined here. Stair climb, 5 meters, 800 newtons. Okay, so we have energy, work, and power, and the example I want to give to pull it all together is the grandfather clock. And my drawings of the grandfather clock are not so good, but I'm going to have you guys look online for some nice images of this. This will be an example where some really good images will help you a lot in your notebook. So let's look at the grandfather clock, and you'll see how it brings all of these things together. And in fact, we haven't talked about a clock yet, so it's going to bring one more element into the mix. So the grandfather clock. Okay. Now, what is that? Just looked at from the outside, it's a big case, 6-7 feet tall, and you have up here your clock, say 3 o'clock right there. So what makes the clock go around? So this is where it gets interesting. There is a weight that you wind up on a pulley or on a spool. So the weight will start up here at the beginning of the week, and as the grandfather clock tells time for the entire week, this weight drops down to here. Okay, so it starts here and drops down to there, which means to wind it up, I have to do work. And when it drops down, it delivers the work again. Okay, now here's where it gets difficult to draw, because we have to imagine there are some gears. I'll just draw some gears here. And these gears are attached. It's a complicated, well, not that complicated, it's a mechanism though. that's attached to the hands of the clock and turns them. So as this weight drops, the gears turn, and eventually they're attached to the hands of the clock, which turns them. So now the question is, why doesn't the thing just spin around and, 10 minutes later, it's spun around and the weight is down at the bottom? There's something that keeps time and that keeps this weight from dropping all at once. And that's a combination of the pendulum. So there's a pendulum, and there is something called an escapement. And this is something I want you guys to look up, get the nice images of this, and make sure you understand what's going on here. You've got a pendulum, you've got an escapement, and basically this thing has some teeth on it, and this gear has some teeth on it, and it swings away and it disengages, and the thing drops down a bit, and then it swings back in, and the teeth engage and stops it from dropping. So pendulum, I'm going to write these out more clearly because I want you guys to really look these up. So you've got the pendulum, you've got the escapement, okay, you got the pendulum, you got the escapement, and then over here you've got the mechanism. And here you have the weight. Okay. So have a good look for some grandfather clock images and explanations with the escapement, pendulum, the weight here, and the mechanism. And let me, by way of demonstration, just show you what I mean by a pendulum. This ruler here would be a pendulum, and there is a period of the pendulum, namely the time it takes to swing. If you build it the right length, you can actually make it take 1 second to swing here, 1 second to swing back. Okay. And I'll explain some more of that. So yeah, this is our project in terms of finding good images. Find good images. As always, print them out and then put them in your notes and show me that you found them. So in terms of our conceptual framework, we raise this weight up and we do some work. And that work, you could say, has been stored. If I stop the pendulum, then that weight will stay there forever. If I start the pendulum back and forth, this weight will do a little click down every second, okay? So you can imagine tiny little clicks all the way down, and 1 week later, it's reached the bottom there. So that is work, and then it's work divided by time, and therefore it's power. During the time this clock is running, a certain amount of power is being used, okay? And so that's energy, work, and power. But we also now have a timepiece. It is a clock, and we have the pendulum to keep time. So I'm going to give us a little discussion of the pendulum. Let me consult the clock on my camera for a moment. Okay, perfect. So we want to find good images of the grandfather clock and these, in terms of these aspects here. So what I'm going to discuss now is time and the law of the pendulum, and then we'll come back around here and do an interesting calculation. So time and the law of the pendulum. So far in our discussion, we have one official unit, and that is the meter. Okay. So now we're going to talk about the unit of time, which is the second. I've already used it. And let's go ahead and draw a pendulum. You guys can do this as an experiment at home. That's the kind of thing actually I like to do in real life here with a pendulum. But you guys build yourself a pendulum simply by taking a piece of string and putting some dense little weight at the bottom. Okay. You suspend it from something. You know, you can suspend it from a door, something where it can swing freely. And you also want to be able to vary the length of your pendulum. So you can have a longer string or a shorter string, or you can have a long string and then wrap it up, and so you just leave a short piece to oscillate. Okay, so the oscillation of the pendulum goes across and it returns, right? And the angle, we'll use a Greek letter theta. That's the amount that when we pull it out to the side, that's the angle it makes with the vertical. So theta is angle that's made with the vertical here. So theta, I'm just going to write angle makes with the vertical. And what you'll discover if you experiment with a pendulum is that the shorter it is, the faster it swings, and the longer it is, the slower it swings. I'm going to give you a formula for the period of the pendulum. So first I'm going to write period, capital T of the pendulum. So the period, capital T here, period of the pendulum, is the time required from when you release it from here to swing over and come back again. Is the time of one complete oscillation. So you let go, it swings over, comes back. If it were a 1 second pendulum or a 2 second pendulum, it would go like this: 1001, 1002. Okay, 1001, 1002. That would be the pendulum swinging back and forth. So here's the formula. Let me give myself some room for the formula. And since everybody has a stopwatch, they have it on their phone or somewhere, you can actually test my formula here and see that it's true. Okay. So the period of the pendulum. Let's see here. Capital T is equal to 2 times pi square root, referring to that picture, the length over a certain letter G that I'm going to define as time goes on. We're actually going to derive where this comes from. For now, you have to accept what this is. L equals the length in meters, and G is a number, 9.8 meters per second squared, and it's called the acceleration due to gravity. Like I said, we're going to get there when we study motion, but we need this right now to talk about, I'll just say acceleration of gravity. Good enough. Okay. So there's our formula. And there's a nice coincidence that this is roughly 2 seconds for a 1 meter pendulum. So let's just do a quick example. Example, L equals 1 meter, T is equal to 2 times pi square root of L divided by the square root of G. So I'm just taking this expression apart here, and I'll just write approximately, what's 2 pi? That's 6.3, approximately 6.3, and the square root of 10, is approximately 3.15. Square root of L. So this approximation is pretty good. That's just about 2 times the square root of L. Now if I chose L equals 1 meter, 2 times the square root of 1 equals 2. Okay. So for a 1 meter pendulum, it's an approximate 2 second period. But the exact one you can get by plugging in 2 pi and then dividing by the square root of 9.8. And you'll see we're close. It's within, a couple percent. It's pretty good. So that's the period of the pendulum. And so if you're going to make a grandfather clock, if you make the pendulum about 1 meter long, little details there, but a simple pendulum, 1 meter long, it's going to be a second there and a second back, a second there and a second back. So that's our law of the pendulum and the period of the pendulum. Okay. Square root of the length. Okay, good. So now we can do a little interesting arithmetic. So it's 2 seconds for a 1 meter pendulum, which is a string this long with a mass on the end. Okay. So what would the 4-second pendulum be? Okay. Well, because of the square root law, you want to get another factor of 2 out of here, so you have to, 2 is the square root of 4. So you would need a 4 meter long pendulum to have 4 seconds. If you wanted a 1 second pendulum, you would take 1/4 of 1 meter, about 25 centimeters, you get a 1 second pendulum. So because of the square root dependence, once you know one of the periods, you can figure out for other lengths. The best thing for you guys, though, is to actually try this. Take a mass, put it on the end of a string, hang it somewhere. When you pull the pendulum out, it's called a small amplitude. You only have to pull it out 15 or 20 degrees. It's fine. So let me write this all as homework. Let's write this as homework. Homework. Construct a pendulum. And I'm going to write the simple pendulum because there's a difference between just this lengthwise mass and a string with a mass on the end. And it's pretty pronounced. So construct a simple pendulum. So don't use a ruler, but it's going to be a string plus mass, as in my picture there. And then test this formula out. So convince yourself. Test the formula. Because, you could actually say make L be 70 centimeters, 0.7 meters, or some length that's not exactly 1.5. And then you'd calculate the period and you would then time it to swing back and forth, say 10 times, and see how that works. So construct a simple pendulum, test the formula, take pictures. So you can take a couple pictures of your pendulum and post them to your notes, put them in your notes, print them out, put them in your notes. Okay, so we got the grandfather clock. There's some images for the grandfather clock, these vocabularies. Then we have this law of the pendulum, very basic device, right? But there's a exact law for the period of the pendulum, and therefore this is the beginning of very accurate timepieces. Okay. So yeah, very important. Consult the time on my camera here. Okay, perfect. So we're going to finish with, and I'm sending you guys out to do this stuff. What we're going to finish with is the power of this pendulum, and you're going to be amazed at how small the power is that it's using. Okay, so once again, pendulum, construct, take some pictures. So the last little topic here is power of our pendulum, or of our grandfather clock. So grandfather clock power. Clock power. Now, there's only one thing we really need to have here. There's the clock. We don't need to know anything about the mechanism. We need to know the weight of the mass and how high we pull it up. And the weight and the height to which we raise these, because we raise it a certain height, and because it's a certain weight, we're lifting a certain weight, of course that's a certain amount of joules. So let's go ahead and say H, and I'll use weight, F, and that height we're just going to say 1 meter. 1 meter is a decent amount of, let's say 1.5 meters, big grandfather clock, 1.5 meters, and the weight, they can be pretty heavy, those weights here. Let's say it were 40 newtons. 40 newtons would, we'll even go with a larger one, 50 newtons. Okay, this is a serious grandfather clock with a good heavy weight, that's like 5 kilograms. Good, okay. So now what's the power going to be? Power is equal to weight times height divided by time. Okay. So we've got the 50 newtons. We've got the 1.5 meters. And we've got the 7 days, because these things will run for a week. This is a realistic example. In fact, they're made to run for 8 days, just in case you forget to wind it up. But you're supposed to wind them up every 7 days. Okay. So can we write 7 days down here? No. We have to convert the days to seconds. So we've got 7 days, and each day has 24 hours, and each hour has 60 minutes, and each minute has 60 seconds. Okay. So this denominator is really large, but you can easily put these into your calculator. You can even do the estimates the way we learned at the beginning of the semester. But this is what I want you guys to find. So you want to find the power with these numbers. This is also homework. Find the power using these numbers, and of course express it in seconds. And it's going to be a very small number, so you have to express it in scientific notation. So we will have had a power of the stair climb, which was roughly 800 watts if we're really trying hard. The power for this, to run this grandfather clock, you're going to find is a very tiny number. Express it 10 to the minus so and so many seconds. Okay, good. And I can always do this too and show it to you guys later, but everybody give this a try. And if you're confused about it, then of course let me know, and I'll return to this. Good, so yeah, we made it really far. And this grandfather clock example, by the way, is going to be the same formula for gigantic hydroelectric power plants, believe it or not. The grandfather clock formula, the stair climb formula, the hydropower formula are going to be, if not exactly the same, very, very close. Good, so let's leave it at that. And next time we'll continue with this material. Actually, I will say one thing. We have the clock swinging back and forth, right? The pendulum. So to get a complete study of what we're doing, we're going to have to study motion. So we'll return to energy, work, and power, and then we'll segue into the study of motion. Good. See you guys next time.